In today's video, we're going to look at some concept called continuity. Here are the goals that we will look at throughout this video. To start with, let's define what continuity is. A function is continuous at an interior point, which we'll call C, of its domain if the following statement is true. If the limit as x goes to c of our function equals our function value evaluated at c. So if the limit as x approaches c of f of x equals f of c, then we have a continuous function at that interior point. Now, if we look at our continuous function at the left interior point, the left endpoint or the right endpoint, we have to modify our definition slightly because we can't say the limit as x approaches c of f of x equals f of c at the left endpoint, because again, for the limit as x approaches c to exist, you have to approach it from the left and the right, and if it's the left endpoint, you have nothing to the left of it to look at. So we modify that and say, okay, for the left endpoint, it's the limit as x goes to c from the positive direction, greater than direction, of f of x has to equal f of c. And for the right endpoint, the limit as x goes to c from the left-hand side of f of x is equal to f of c. So one-sided limits work only at the endpoints of a function. Now, if a function is not continuous at point C, we say that f is discontinuous at C, or C is a point of discontinuity. There are many types of discontinuity, but in this class we'll focus on 3. The first type of discontinuity we'll focus on is point, or sometimes it's called removable discontinuity. So point discontinuity, removable discontinuity. This is when the limit exists at a point, but the function value is not equal to the limit value at that point. So in function notation, that means that the limit as x goes to c of f of x exists, but the limit as x goes to c of f of x is not equal to f of c. Okay? And graphically, you can see that here, and instead of c, the graph used a. But as you can see from this, at x, the limit as x approaches c of f of x is L. So they're approaching that value. But f of c does not exist because it's an open circle. And then, so that has what's called a removable. That point has been removed. So removable or point discontinuity. Same thing in this second graph here. You can see that the limit as x approaches our a or c value here exists. It's at a height of L. But the function value, f of c here, is equal to m. So they're not equal to each other. So we have removable or point discontinuity there. The second type of discontinuity we'll learn is jump discontinuity. And that's when both one-sided limits exist. The limit from the left exists, the limit from the right exists, but they have different values. So that means, and I'll use the a instead of c this time. So that is the limit as x approaches a from the left of f of x is not equal to the limit as x approaches a from the right of f of x. And that's how you know you have jump discontinuity. Here's example jump discontinuity. Limit from the left is equal to L. The limit from the right is equal to M. So they're not equal. So our function has jumped. So that's jump discontinuity. All right, our third type of discontinuity is called infinite discontinuity. And it occurs when both one-sided limits are infinite. That is the limit, and I'll use a again, as x approaches a from the left of f of x is equal to either positive or negative infinity, and the limit as x approaches a from the right of f of x is equal to positive or negative infinity. So it has to be happening from both of them. One could be infinity and the other one not, and you don't have infinite discontinuity. In that case, you would have jump discontinuity if one of those one-sided limits was not infinity but a number instead. Excuse me. Graphically, infinite discontinuity occurs when the graph has vertical asymptotes. Okay, so here are 3 examples of infinite discontinuity. In the first graph, you see we have a vertical asymptote, and the limit from the left is going to negative infinity. The limit from the right of A is also negative infinity, so that's infinite discontinuity. Here, the limit from the left and the limit from the right is going to positive infinity in both directions, and so infinite discontinuity. In our third graph, the limit from the left is going to positive infinity, but the limit from the right is going negative infinity. They're still going, both sides are going to infinities, so we have infinite discontinuity. Okay, so let's try a problem graphically. All right, so based on the graph, determine where the function is discontinuous. And then at each point of discontinuity, we're going to state the type of discontinuity and where it is discontinuous. If the discontinuity is infinite, we're going to find the equation in the asymptote, and we're going to state the intervals in which the function is continuous. All right. So first, let's focus at this x value of -4. So I notice here at -4, I have jump discontinuity. So I got jump discontinuity at x equals -4. How did I know that this is jump discontinuity? Well, I know it's jump discontinuity because the limit from the left of -4 is not equal to the limit as x approaches -4 from the right. The limit from the left is 2, the limit from the right is about 1/2, so they're not equal to each other. All right, next point of discontinuity is at what? Here we have removable or point discontinuity, whichever one you want to call it. And how do we know we have point discontinuity? Well, the limit as x approaches 1 of f of x exists. It happens to be a -1, but that is not equal to our function value at 1, because the function value at 1 is undefined. Okay, next one is at x equals 3. It's another jump discontinuity. And again, we know that's jump discontinuity because the limit from the left of 3 is not equal to the limit as x approaches 3 from the right. And then next one is x equals 6, and that's infinite discontinuity. And we know it's infinite discontinuity because the limit as x approaches 6 from the left of f of x equals -infinity, and the limit as x approaches 6 from the right of f of x is equal to positive infinity. All right, and then there is one more point of discontinuity here, and that's at the endpoint of 10. Okay, and this is again point discontinuity or removable discontinuity. And that's because the limit as x approaches, and because it's the endpoint, I don't have to do this point discontinuity as the limit, but the limit as x approaches 10 from the left of f of x is not equal to the function value at 10. Now the left endpoint exists because the point is filled in, so that one works. So those are all points of discontinuity. And the last thing it asked us to state is state the interval in which the function is continuous. So I'll write that down here. Continuous. All right, so it's continuous starting here at -8, and we include -8, so we do brackets, all the way into that -4, and then from -4 all the way to 1, from 1 to 3, whoops, 1, 2, 3. I need a comma there. And then from 3 to 6. And finally from 6 to 10. But this time 10 is not included, so I have parentheses, not brackets, at that end point. All right, so that's graphically figuring out limits, figure out where it's continuous or not. Now we're going to look at some algebraic techniques of using the definition of limits. So, a definition of continuity, to prove that a function is continuous at a given point. So, there are 3 conditions that need to be satisfied in order to prove a function is continuous at a given point. First thing is that f of a exists. So the function value exists at the given point a that we're looking at. The second one is that the limit as x approaches a of f of x has to exist. And usually to figure that out, we'll have to look at the limit as x approaches a from the left needs to be the same as the limit as x approaches a from the right. And that'll tell us that the limit exists. And then the last requirement, the function value exists, the limit value exists, and the final requirement is that the limit of x approaches a of f of x has to equal the function value. All right, so now let's look at our first example here. We're going to use this definition of continuity to prove that the function is continuous at the point x equals -1. So first we figure out f of -1. So we got to see if the function value exists. So we just do direct substitution. Excuse me about my nose, but my allergies are just bugging me today. Let's see. So that's -4 plus 5. So that's 1 over 12. That's a value. So therefore, f of -1 exists. So we proved our first condition. Now let's try our second condition. Limit as x approaches -1 of our function. All right, let's try direct substitution. And that is 1/12. So therefore, the limit as x approaches -1 of our function exists. And both of those answers was 1/12. So, since the limit as x approaches -1 of f of x equals f of -1, f of x is continuous at x equals -1. So you've proved continuity at that point. All right, let's try one more. So first here, I gotta show that g of -6 exists. Well, by our definition here, g of -6 is 7. So that equals 7. So g of -6 exists. So prove that statement. Now I gotta find the limit, but this time, to find the limit as x approaches -6, I gotta do the limit from the left. Which would say I need to use the top equation using direct substitution. I get 19. And then I need to do the limit as x approaches -6 from the right. Looking at our piecewise function, that tells me I should use the bottom equation. Again, doing direct substitution. That gives me -222. So therefore, the limit as x approaches -6 of g of x does not exist because the limit from the left and the limit from the right are not the same value. So therefore, g of x has, and then the limit of the left does not equal the limit from the right, so this is jump discontinuity. At x equals -6. So that'd be my conclusion. Okay, sometimes we can just look at the type of function and figure out continuity and information about it. So there's certain functions that are continuous everywhere. So we just kind of memorize these and we kind of help us a little bit. So the constant function, f of x equals a constant, is continuous everywhere. It's a horizontal line. The identity function, f of x equals x, is continuous everywhere. In fact, any polynomial function, y equals f of p of x, polynomial function, is continuous everywhere. So that's nice. Now, a rational function, when you have a polynomial divided by a polynomial, p of x divided by q of x, is continuous for every value of x where the denominator is not equal to 0. So it's continuous everywhere except that the vertical asymptotes are the holes in the graph. So to figure out which one you have, if you have a rational function, first thing you're going to do is you're going to simplify the rational functions by finding the factors of each of the factors of p of x and the factors of q of x, cancel anything out. If you cancel something out, the factor that you cancel out will tell you where you have a hole in the graph, and that would be removable discontinuity. And if you then if you're looking at the simplified rational function, any denominator term that does not cancel out, you set that equal to 0, and that'll be your vertical asymptote. It occurs whenever that denominator equals 0, and that would give you infinite discontinuity points. Okay. Now, if f is a continuous function and g are continuous functions at x equals a, then the following will also be continuous. So if you take f of x and you raise it to a power, where n is a real number, this is continuous at x equals a, whatever it is defined at that number. If you take a continuous function and you add another continuous function, or a continuous function minus a continuous function, it is continuous at x equals a. Since f and g are continuous at x equals a, if you take f times g, it is also continuous at f equals a. And if you take f divided by g, g, not q, it will be continuous everywhere. State whether or not each of the following functions is continuous. If not, state where the discontinuity occurs and the type of discontinuity. Oh, I forgot to find the asymptotes from this other one. Here's our infinite discontinuity. So our equation of our asymptote is x equals 6. That's the equation of the asymptote. Because here is asking us to find the equation of the asymptote as well. All right, so this f of x for part A is a rational function. So points of discontinuity is where the denominator equals 0. So let's see if we can factor that denominator. And it factors to 2x plus 1 and x minus 1. So setting this equal to 0, x equals negative 1/2, and x equals 1. So we have infinite, that vertical asymptote says infinite discontinuity, so we have infinite discontinuity at x equals negative 1/2 and at x equals 1. And we have vertical asymptotes at x equals negative 1/2 and x equals 1. All right, let's figure out if we have discontinuity here. Okay, so the top function is x squared minus 9 over x minus 3. That's the difference of squares on top. And then the x minus 3's cancel out, which leaves us with x plus 3. So since we cancel that out, so the factor we canceled out was x plus 3, which gives us x equals 3. And if I plug in 3 into this equation here, I get 6. So I have a hole in the graph at 3, 6. Alright, so that tells me the limit as x approaches 3 of h of x is equal to the limit as x approaches 3 of our function, which we just simplified that already to be 6. So our limit exists, it's 6, but our function value at 3 is 8. So those are not equal. So since the limit is not equal to the function value, we have a removable or point discontinuity. We knew that since the limit as x approaches 3 of h of x, I believe it was h of x, yeah, is not equal to h of 3. All right, last one here, g of x is 3x cubed plus 2x squared minus x plus 10. That's a polynomial, so this is continuous everywhere since g of x is a polynomial. I'm using that rule right here. Sometimes you'll have a piecewise function and you would have to find the values of a and b that makes this function continuous. And so to check continuity of each individual piece of the piecewise function, and then possible points of discontinuities will occur when one piece changes to the other piece. So in order to make it continuous, we're going to have to set our left-hand limit equal to our right-hand limit. So that's it. Basically, we'll be solving the limit as x approaches a from the left of f of x, setting it equal to the limit as x approaches a from the right of f of x, and then solving for our a and b. All right, so here's an example. This is our f of x definition. Now notice that our pieces are broken up at 1 in between the top and the middle function, and at 2. So we're going to have to do this twice, at x equals 1 and x equals 2. So first thing I notice is that since x plus 1, ax plus b, and 3x are polynomial functions, they are continuous everywhere they're defined. So I don't have to look at any other possible points of discontinuities. So the only points of discontinuities that occur is it could be at 1 or at 2. So to check at x equals 1, I want to set the limit as x goes to 1 from the left. And from the left, looking at my piecewise function, should be the top equation. Has to equal the limit as x approaches 1 from the right. And from the right, that will be my bottom equation, my middle equation. I'm going to evaluate this limit using direct substitution. And that'll give me 2 is equal to a plus b. Now, as far as I can do with that as now, but then I have my x equals 2 I can look at. So at x equals 2, I need to figure out the limit as x goes to 2 from the left. Smaller than 2 but close to 2 is the middle equation. That needs to equal the limit as x goes to 2 from the right, which would be the bottom equation. Using direct substitution, place every x with 2. I get 2a plus b equals 6. So I have, at this point now, we have a plus b equals 2, and 2a plus b is equal to 6. So we have a system of equations that we can solve this system of equation. And let's say I'm going to multiply the top equation by -1. So negative a minus b equals -6. Add these together, I get a is equal to 4. If a equals 4, choose one of the original equations, and a is 4. So b is -2. So this function will be continuous if a is equal to 4 and if b is equal to -2. So if I replace a with 4 and b with -2, this piecewise function will be continuous everywhere. All right, last thing we're going to learn is the intermediate value theorem, abbreviated IVT. A function y equals f of x that is continuous on a closed interval from a to b takes on every value between f of a and f of b. That's what the intermediate value theorem states. Okay, so think of it like this. Okay, so we have some function. All right, we'll do this function here. Okay, and we will let this be a, and this will be our b. All right, so at f of a, here is our, at x equals a, here's our function value at f equals a. And then at b, here is our function value f of b. Now, since the function is continuous, I know that I will have a corresponding dot everywhere on this function for every y value from here to here. From every y value from here to here, I must have a corresponding, at least one height on our function. Now, we might have more than one height, but we have at least one height on our function. So that's pretty much what the intermediate value theorem states. Now, when you solve a problem using the intermediate value theorem, since you're using the intermediate value theorem, there are some steps that you have to go through and show that you're using this theorem. So first step that you have to do is you have to write a condition statement. And that shows that the function is continuous on the interval. Because notice our requirement for this function, this theorem, is a function that is continuous. Oops. Switch over. That is continuous on the closed interval. So we have to show a statement telling us our continuity, that it is continuous. That way we can apply the intermediate value there. Excuse me. Okay, then we're going to do our work. And then we're going to evaluate our functions at our endpoints. That's going to be our main work. And then you're going to end with a conclusion statement that shows that the desired y value is between the endpoint function values. All right, so let me show you how this would work. There's two types of ways this will set up. Example 5 and 6 will show this. So example 5. Using the intermediate value theorem to show that there exists a number c in the given interval such that f of c equals m, then find the value of c. Okay, so you have to start with your condition statement. So we have to prove continuity, pretty much. So I look at our function, and f of x is x squared minus 4x plus 6. It's a polynomial. So since f of c is a polynomial, it is continuous everywhere. Okay, so that defines it as everywhere. But I don't really care in this problem about it being continuous everywhere. It wanted us to look on this closed interval from 0 to 3. So now I have to take this everywhere from negative infinity to infinity and bring it down to what I'm focusing on this problem. So then you'll say that is f of x is continuous on the interval from 0 to 3. Done. So that's our condition statement. We approve continuity on our closed interval. Step 2 is the work. So I notice my left endpoint of my interval is f is 0. So your first work is to figure out your function value at 0. Just do direct substitution, and you get 6. Then you find your function value at the other endpoint. Do direct substitution here, and you get 3. Now, we wanted to prove that the function value, at least some c value where the function value is equal to 4. So what you have to do is you have to look at these results you got in your work here. And the one that you're looking at has to be between those two values. If it's not, you can't use the intermediate value theorem. So it has to fall between that. So since 3 is less than 4, which is less than 6. So our two endpoints, the value that we're focusing on, 4, is between our two endpoints. I can use the intermediate value theorem. So by the intermediate value theorem, there exists some c such that f of c equals 4. Now we got to find that value of c. Well, that's easy. Go back to your function, which is x squared minus 4x plus 6, and set that equal to 4. And we're going to solve this. So I need to subtract 4 from each side. All right, and I asked myself, okay, is there a function value? Factors of 2 that add to equal -4? No, so this does not solve by factoring. And so I got to do the quadratic formula. We'll go down here. I don't have enough room there. So we got x squared minus 4x plus 2. Okay. So a is equal to 1, b is equal to -4, c is equal to 2, x is equal to opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Alright, that's 16 minus 8 over 2. That's square root of 8, which is 2 to the square root of 2 over 2. X equals 4 plus, 2. Let's factor out our 2 there. 2 plus or minus the square root of 2. Then look at our interval we look at. It's from 3 to 6. 2 minus square root of 2 is not in the interval. 2 plus square root of 2 is in that interval. So our c value is 2 plus the square root of 2. We throw out the -1 because it's not in our interval from 3 to 6. I'm sorry, our interval from, not 3 to 6, our interval from 0 to 3. All right. Most often, you'll use the intermediate value theorem to find the zeros of a function. Basically, that's where the function value, f of c, is equal to 0. So it's the same as this, but now m is just 0 when it asks you to find the zero of the functions. Alright, so show that this function must have at least one 0 between -2 and 6. So condition statement goes first. Since f of x is a rational function, it is continuous everywhere it's defined. And it's defined everywhere except can't divide by 0, so set the bottom equal to 0. So that's -4. That is, f of x is continuous from negative infinity to negative 4, union negative 4 to infinity. Bring it down to the interval we're looking at. Notice that negative 2 to negative 6 is included all the way inside this given interval here. So that is f of x is continuous on the interval from negative 2 to 6. So we've shown our prove continuous. So that's the first step of the intermediate value theorem. Second step, evaluate the function at its two endpoints of the interval. So we're going to do direct substitution. And I get what? Negative 4 over negative 2, which is negative 4 over positive 2, which is negative 2. And f of 6. Oh, that should be a minus sign. That gives us 2/5. 0 is between negative and positive, so yes. So conclusion statement, since negative 2 is less than 0, which is less than 2/5, by the intermediate value theorem, there exists at least one 0 in this given interval. In the interval negative 2 to 6. And sometimes I'll ask you to find the 0. And you do like we just did the last value to find that value, but this time it didn't ask you to find it. So that's all I need to do for this problem.